Hello everyone, I'm Dr. Shafiq and I would like to welcome all of you in this video session. Basically in this session I'm going to show you some of the example problems from lateral arc pressure. Okay, I posted another video for the theory of lateral arc pressure. Here I'm going to show some of the example problems so that you will be able to understand better, and that would be also helpful to solve some of the homework problems for you. Okay, now let me share my screen with you. So this is problem number one, very simple one. You can see this one is for at rest pressure, means like when the wall is not moving at all. Okay, it's kind of standing, upright in that situation. So this one is asking the soil profile at a site is shown figure number one. Find the total horizontal normal stress at A and B, assuming at rest condition. One thing I must have to say here that from the theory, you can only find out the lateral pressure from the soil. But if you have water table there, you can understand that there would be pressure from the water table to the wall too. Now, from the theory, you can understand that basically your water pressure is equal in every direction. Okay. Now let's move forward to our board and try to solve that one there. Okay. So this is problem number one. So you can see here that this is point A, which is 2 meters below the surface, and B is actually total 3 plus 4, 7 meters from the surface. Okay, so to do this problem, just try to find out the sigma A prime, the effective stress at point A, which is actually gamma into H, (16.5) multiplied by 3, not 2, which is basically 33 kilonewton per meter square. So your sigma H has to be, this is your coefficient given here. So K naught sigma A prime, which is 0.45 multiplied by 33, that's actually 14.85 kilonewton per meter square. Now you can see here there is no water table here, so pore water pressure is actually 0. So your total pressure is equal to your effective pressure plus U. So U equal to 0, so that remains 14.85 kilonewton per meter square. Okay. Now, if you try to do that one for point B, then the effective stress at B would be, you can see 3 meter and 16.5 into 3 meter plus 19 minus 9.8, that's the submerged unit weight, into 4. And that's basically 86.26. So your horizontal stress from the soil, that would be K naught. Actually, this is K naught 2, K naught sigma B prime. So for this one, you can see this layer, actually your K naught is 0.55. So this one would be 0.55 multiplied by 86.26, which is basically 47.44. And you can see at point B, this is underwater, and this is 4-meter water. So that your pore water pressure here is gamma W, HW, which is 4 into 9.8. That's actually 39.24 kilonewton per meter square. Now you know from the property of the fluid that fluid usually exerts pressure, same pressure at every direction. So it doesn't matter whether it's vertical or horizontal pressure. So the horizontal pressure is same as vertical pressure. So your total pressure at horizontal pressure at B, that's actually so 47.44 plus 39.24. That's actually 86.68. Okay, let's move forward. So this is example number 2. Okay, this one is basically active pressure, and we are going to follow that one based on Rankine's method. And one thing important here, that the backfill is flat here. This is your wall and your backfill is here, which is not making any angle with that. So this is kind of flat. Now, if I read this one, then determine the magnitude and the location of the active thrust on the smooth vertical wall shown in figure 2. When this one is saying a smooth vertical wall, this is kind of implied that you have to use the Rankine's method, because Rankine's method assumes that there is no friction between the soil and the wall. Okay. On the other hand, the Coulomb's method assumes that there is a friction between the soil and the wall. Okay, so it's kind of implied. If they say that the smooth vertical wall, then basically you have to follow the Rankine's method. Okay, if they don't say that one and they give you a frictional angle there, then basically you have to follow the Coulomb's method. Okay, now let's go to the board and try to solve that one there. Okay, so this is the drawing for problem number 2. You can see this is like asking to determine the magnitude and the location of the active thrust on the smooth vertical wall shown in figure. So assume that the entire backfill is in active condition. Okay, so to do that, actually what we usually do, you can see that phi has changed from here to here. So your active coefficient will be changed, because we know that Rankine's method, and again, that they're saying that the smooth wall, which means like there is no friction between soil and wall, which means actually you have to follow the Rankine's method. Okay. Now, according to Rankine's method, you know that your Ka is equal to 10 square 45 minus p by 2. Okay, so for this layer, you can see Ka1 is basically 10 square 45 minus 34 by 2, which is basically 0.283. And for layer 2, your coefficient is 10 square 45 minus 36 by 2. So this one is actually 0.26. Okay, so let me write it down here that your Ka here is 0.283 and Ka here is 0.26. Okay. Now, since there is a change in property here, so at a depth of 4 meters, so I'll try to take the overburden stress at point here, here, and here. Okay. So let's say we are measuring here to Z is the depth. So at Z equal to 0, you can see your overburden pressure is basically gamma H. So H equal to 0. So this one is 0. Okay. So your sigma H is also 0. Now at Z equal to 4 meters, you can see there is no water table here, so I'm not writing like effective stress and total stress here. If we see water table there, then basically we have to take the effective stress, okay, and then add the whole water pressure. For this particular case, there is no water. This means like your core water pressure is 0, so your effective stress is equal to your total stress, right? So here, this one is, you can see gamma H, which is 16.5 multiplied by 4. So that's 66 kilonewton per meter square. Okay. So your effective stress for the top layer, just a little bit above this interface here. So this one is like this layer here, right? So your sigma H for upper layer, let's say our top layer, is actually your Ka into overburden stress. So this is 0.283 into 66. That's basically 18.68. Now we can see if I just go a little bit below that interface, actually Ka has changed from 0.283 to 0.26, right? So your sigma H for the bottom layer is actually Ka2 sigma naught, that's actually 0.26 multiplied by 66. That's basically 17.16. Now we are going to find out, like, hey, what would be the horizontal, vertical and horizontal pressure at point at the bottom here. Okay, so at z equal to 7 meter, your overburden pressure is gamma h, so which is 16.5 multiplied by 4 plus, actually this is, both of them is 16.5. Okay, so this is 16.5 into 2. No, it's into 3. Sorry. So that's actually, we can just say 16.5 into 7. So the horizontal pressure at a depth of 7, that would be Ka sigma naught, and we know that Ka is 0.26 into Ka is 16.5 into 7. Total, that's actually 30.0. Okay. Now they're asking, like, not the pressure, they're asking like the force working per meter length of that one. So let me draw that one here so that you can understand easily. Okay. So this is the diagram of pressure. Okay, so you can see here is 0. Here is 18.68, and when you go to a little bit down, then 17.16, and when you are coming, then this is 30.03. So the pressure is actually working in this direction, right? So total force would be equal to the area of the horizontal loading diagram. Okay, so to do that, actually what I'm gonna do is like make 3 areas here. Let's say this is my area 1, and then this is area 2, and this is area 3. Okay, so for area 1, my force is working here. Let's say this is F1, which would be half into this, right? So half into 4 into 18.68. So that's basically 37.36 kilonewton. And the distance from here to here is basically 3 plus 1/3 of 4, right? So 1/3 of 4 is basically 1.33. So the total distance from the bottom is 3 plus 1.33. So that's 4.33. So if I want to show, like for area 2, the force is here, which is basically 3 into 17.16. So F2 is equal to 3 multiplied by 17.16, which is basically 51.48 kilonewton. And the distance from here to here is half of that, which is 1.5 meter. Okay. Now for area 3, this is, let's say, F3. Which is basically half into this distance into this distance, okay? So this is 3 into 30.03 minus 17.16. So that's basically 19.31. And the distance from here to here is basically 1/3 of this one, which is basically 1 meter. Okay, so I have 3 parallel forces there. So the resultant force P is basically, or let's say resultant force F is equal to F1 plus F2 plus F3. So which is 37.36 plus 51.48 plus 19.31. So total is 108.15 kilonewton per meter length of the wall. Okay. Now, where is the location of this, like resultant force? So let's say here is the resultant of your. That's actually F, which is equal to 108.15. Let's say this distance from here to here is D. So if you take a moment of the resultant force from the bottom, that should be equal to the moment of all the components together, right? So here we can just take a moment of that, and we can see that F multiplied by D is equal to F1 D1 plus F2 D2 plus F3 D3. Okay, so 108.15 D is equal to F1 D1, so 37.36 multiplied by the distance, which is actually 4.33 plus F2, which is 51.48, and the distance of F2 is 1.5 plus F3, which is 19.31, multiplied by the distance here, which is 1. So your D is basically, if you add all of them, that's 158.3 divided by 108.15. So this one is 1.46 meter. So the distance from here to here is 1.46. So that's basically your answer. So the horizontal force working per feet length of the wall is 108.15, and that's working 1.46 meter from the bottom of the wall. Okay, let's move forward. This is example 3. Okay, again, this is active pressure, and we are going to follow the Rankine's method. But here, this one is slope backfill, which means that like the backfill here, this is your vertical wall, and the backfill here has an angle alpha with the horizontal. Okay, this is basically a generalized case. Now, the problem is saying that a 6-meter high smooth wall, this is 6-meter high smooth wall, retains a C-Phi soil. C-Phi soil means the soil which has C as well as Phi. Means like this is actually the mixture of the sand and clay, okay? Which is most of the soil is kind of C-Phi soil. Purely clay or purely sand is actually much less than your C-Phi soil, okay? Then they're saying that your C prime is 10.5 and your phi is 15 degree. Gamma, unit weight of the soil is 17.5 kilonewton per meter cube, and the backfill slope is 5 degrees here. Okay, so first of all, they are asking you to find out the tensile crack, distance of tensile crack from the top. Okay, so you have to follow the equation 16.34 in your book. Okay, I'm going to show that one in the next page. Okay, then also asking determine the active pressure variation with the depth based on equation 16.32 and equation 16.33. And third, it's asking like determine the magnitude, location, and direction of the resultant active thrust PA. Okay. Now let's see the first one first, like determine the depth of tensile crack here. So from the equation 16.34, the depth of tension crack is 2c prime divided by gamma root over 1 plus sine phi prime divided by 1 minus sine phi prime. So our C prime and gamma and phi prime is given. You just plug all those values here and you will get the depth of crack, tension crack, which is 1.56 meter. Okay. Now let's try to do the second part like B. So for second part, they are asking you to find out how your sigma A varies with your Z, means your depth. Okay. Now you can see for the generalized case, actually your Ka prime is basically a big function here, which is your equation 16.33. Okay. They have a table there, okay, to find out how to get your Ka prime. But actually, I also posted a Excel file there. And if you plug the basic information like your phi prime, your alpha, as well as like C prime by gamma Z, which actually varies with your Z. So if you have that one, then basically you can plug all those things on that equation and you can find out your Ka prime. It's a little bit difficult to calculate your Ka separately all the time. So I'll just ask you to use the Excel file that I posted there to find out your Ka prime if you have any problem like that. Okay, once you get your Ka, then basically you just plug that one in this equation here, that gamma Z Ka prime cosine alpha, then basically you will get this column here. Okay. So once you get this one and this one, then basically you can just draw a chart here and you can see this is your sigma A prime with your depth. So first 0 to 1.56 meter, that's your tension crack zone. So at that part, actually, your soil is a little bit away from the wall because wall is moving like this. So the soil will be there. If it is sand, this one will just go like this. But since the soil has cohesion, so this one will still like here, okay? So it's not creating any pressure on the wall. Okay, on the other hand, we can see the pressure is coming just below the tension crack, and this one is kind of linear because this is just one layer of soil. If you have more layer of soils and their properties are different, then basically you will see the slope of that line will change. Okay, now let's move forward. This is example number 4. This is active pressure, but here we are gonna follow the Coulomb's method. Okay, so this one is saying refer to figure 4, which is here. Your H is 6 meters from here to here. Your gamma unit weight of soil is 17 kilonewton per meter cube. The soil here, you can see phi prime is 36 degree. Your cohesion is 0. Your beta is 85 degree. This is basically your beta, 85 degree. If it is vertical, then your beta would be 90 degree. Okay, and then you can also see that your friction between soil and wall, delta prime, is 2/3 of your phi prime. Okay, if it is 36, this one would be actually 24 degrees. Then this one is also saying that assume that the backfill is in active condition. Okay, so use the Coulomb's equation to determine the magnitude, location, and direction of the active thrust on the wall. Okay, now it's same thing, only difference is your Ka here. So you try to find out your Ka from this equation. And once again, you can see it's a big equation. So I also, included that one in the Excel file that I posted there. Okay, so you can just change your value of, beta, phi prime, alpha, and you will get your Ka from there. Once you get your Ka from there, then you can find out the force that's coming from that. Ka actually is half into Ka into gamma h squared. Okay, same as before. Okay, now the good thing is like they put a table of that in your book, but they varied your delta prime only like 2/3 of your phi prime and half of your phi prime. If it is, let's say, uh, uh, 1/4 of your phi prime, then the table doesn't show you like the results there. So basically, you have to use the formula there to find out your Ka. Okay, so for this particular problem, actually, we have the value in the table. You can see your delta prime is 2/3 of phi prime here, and then your alpha is 10 degree, your phi prime is 36, and your beta is 85. Then basically you can see your Ka is basically 0.3072. Once you get your Ka, finding out the force is very, very easy. Just plug that one in your equation. Okay, but the problem is like if you're, let's say they gave you like 90, 85, 80, if your beta is 83, then basically you have to do a lot of, like calculation here, like interpolation to find that out. So to make that one easy, actually, I just posted the Excel file, which has this equation set up there. If you just plug all those values of alpha, phi, beta, and delta, then basically you will be able to find out your Ka from there. Okay. Once you get that one from there, then basically that's your Ka 0.3072. If you use that one in that equation, you just get 94 kilonewton per meter length of the wall. Okay, in this direction, this is 1 meter. That's what it's saying. Now, the difference between like Rankine's method and Coulomb's method in terms of the active force is like both the cases, this one is 1/3 from the bottom if it is like a triangular, like distribution, right? But for active pressure, let's say for Rankine's method, the force is always parallel to the top surface of the backfill soil, okay? But in Coulomb's case, this is completely different, okay? You can see here that this is the line here, internal line that's in touch with the soil. You have to draw a vertical line here. Okay, the top one is horizontal line, and the next one here, this is actually vertical line here. And your active force is always making a angle delta prime with this perpendicular line. Okay, so that's basically you have to remember, like when you were dealing with Coulomb's method. Okay, now let's see some of the problems from passive force. So here I'm going to do the same problem following Rankine's method and same time with Coulomb's method, and try to see that how that result differs from each other. Okay, so that's the problem here. This one is saying that a 3-meter high wall is shown in figure 5. Determine the Rankine passive force per unit length of the wall, and example 6 is same thing, but only change is like you have to do that one following Coulomb's method. Okay, now you can see here that actually this is a vertical wall, and then this one is flat here, and you have two different type of soils here. One is sand, which is 30° phi, and cohesion is 0. The other one is C phi soil, means like this one has phi as well as C. So your phi prime is 26° and C2 prime is 10 kilonewton per meter. Okay. Once again, for Coulomb's method, you have to find out your Kp, means like your coefficient of passive force, using a bigger equation. And I already posted that one in that Excel file so that you can calculate your passive pressure quite easily. They have also a table for that, but actually I see that phi prime 26 is not given there. They have like 20, 20, maybe 5, 30, something like that, but not 26. So if it is not given in the table, then basically you have to use the formula. And it's kind of like troublesome to calculate that big equation every time. So it's always better to keep an Excel file there, so that if you change the basic parameters there, then it will automatically calculate your coefficient there. Now let's go to the board and try to see how we can solve the problems over there. Okay. So this is the figure for problem number 5. You can see here that you have a water table here, and this is your ground level. And this is one type of soil, this is different type of soil, because here C is equal to 0, here C equal to 10 kilonewton per meter square. So it's a C-P soil. On the other hand, this one is kind of sand or silt. Okay. Now, this one is saying that this 3-meter high wall, determine the Rankine passive force per unit length of the wall. Okay, passive force. The other one we did previously, like problem number 2, that was actually active force. Now it's kind of like they're saying that it's we have to find out the passive force. Okay, so first of all, I have to find out that Kp here, which is 10 square 45 plus p by 2. So our p is 30. So your Kp will be actually 3. For here, my Kp would be 10 square 45 plus T by 2, so 26 by 2. So this one is actually 2.56. Okay. Now you have to remember that like this one is a very simplified problem because this one here is vertical, the wall is vertical. At the same time, you can see there is no angle here, so it's flat. In that situation, basically, we can use these formulas, right? If we have an inclination, or if you have like this one little inclined here, in that situation, basically, we cannot use this formula. So we have to use the generalized equation there. Okay. Now let me write it down like my Kp here is 3 and Kp here is 2.56. Okay. So at a depth of 0 feet, Z, which is measured from here to here. So at Z equal to 0, our sigma overburden is gamma H. So that's actually 0. So your horizontal or active force is also 0. Now at Z equal to 2, just above the water table, okay, just above the water table. So let's say at top layer, so you can see here that your sigma is basically gamma H, which is 15.72 multiplied by 2. So this is 31.44. Now we know that actually the passive force sigma P is Kp sigma naught plus 2c root over Kp. Okay. So my sigma P at Z equal to 2 has to be 31.44 multiplied by 3 plus 2c, c equal to 0 here. So basically this part is 0. So this one is actually 94.32. Okay. Now, if I go a little bit down up here, so at Z equal to 2, but for bottom layer, my sigma naught overburden pressure remains same just above and below here because this distance is very infinite, small and very little. So the vertical pressure is not going to change. But you can see in your passive pressure here will change significantly because now I have C here and my P is a little bit different, so my KP is also different. So this one has to be KP, so 2.56 into sigma, which is 31.44. Now I have this part here. So C is 10, and this one is 2.56. So if I add that one, that's actually 112.49. Okay. Now again, I can just find out that's actually for the bottom at Z equal to 3. Now I have a water table here, so I have to find out the vertical pressure in terms of effective stress, and I will add the whole water pressure to find out my total horizontal pressure. Okay, so here at Z here, my sigma naught prime is basically this one plus this 1 meter, so actually 31.44 plus gamma H, so 18.86 minus 9.8 into 1. So this one is basically I don't know. I have to calculate that one here. So I'll just leave it like that. So once I try to find out my sigma P here, so I have to use this formula here, Kp sigma naught. So Kp, that's actually 40.49. This one is actually 14.49. So this one has to be 2.56 into 40.49 plus 2C root over 40.49. No, root over 2.56. So this one is actually 135.65. That many kilonewton per meter square. So now you can find out actually this is my horizontal pressure only from the soil, okay? But my pore water pressure is actually gamma WHW, which is actually 9.8 into 1. That's actually 9.8 kilonewton per meter square. Okay. Now, the same way I can draw the pressure triangle or a stress triangle, and then I can just find out the force for that loading diagram. Okay. So let me draw the pressure diagram. So this is the pressure diagram for this problem, what we already find out from here. This is for the pore water pressure here. So I can just again divide that one into 3 different areas. And that's actually 4 areas, including the water table. So my total pressure or total force working per unit length of the wall is just the area of this pressure diagram, right? So if I do that one here, total pressure EP, so for this one is half into 2 into 94.32. For the second one is this multiplied by this one multiplied by 112.49 plus this one here, which is half into 1 into 135.65 minus 112.49 plus half into 1 into 9.81. So which is basically 223.3 kilonewton per meter length of the wall. Okay. They didn't ask here that the location of the force. If they ask that one, then basically you have to take a moment and try to find out what would be the resultant force. Okay. Now let's move forward. So this is the drawing for problem number 6, okay, which is basically the same problem like what we did in problem number 5. Only difference here is like we have to find out the passive force per unit length of the wall following Coulomb's method. Okay, so once you have to do the Coulomb's method, then basically we have to know what is the friction between the soil and the wall. Okay, so here actually they gave you this value like your delta prime is actually half of your much longer time. I'm just putting the value here. You can just check that one in the spreadsheet. Okay, so here your Kp z equal to 0, your sigma is 0, so your sigma 7.2 multiplied by 2, that's actually 31.44. So according to Coulomb's formula, your sigma h is just your Kp sigma naught. Okay, there's not like 2c root over k. That's only applicable for Rankine's method. Here, you just have to multiply with that factor, and you can find out your sigma h over there. So you can see this is 4.977 multiplied by 31.44. That's actually 156.48. Now, if I say like just add z equal to 2 for bottom layer, then you can see this one remains same, but my sigma h would be now 3.787 multiplied by 31.44, which is basically 119.06. And again, at z equal to 3, your sigma naught is basically 31.44 plus 18.86 minus 9.8, that's actually 40.49. So your sigma h would be 3.787 multiplied by your sigma naught, 40.49. So that's actually 153.34 kilonewton per meter square. And once again, you know your pore water pressure is actually 9.81, right? Now let me draw the pressure diagram, okay? So here is the pressure diagram you can see here, okay? So now I have to add that area under the pressure diagram to find out the force, horizontal force that working per unit length of the wall, okay? So if I do that one, let's say this is area 1, this is 2, this is 3, and this is 4. So I can say that my PP, passive force pressure, is, if you take this one, that would be half into 2 into 156.48 plus this area, which is 119.06 into 1. This area is half into 1 into 153.34 minus 119.06 plus this area, which is half into 1 into 9.8, which is the total force is basically 297.6 kilonewton per meter. Okay, so that's the answer from the Coulomb's method. And you can remember, like from the problem number 5, actually this one was 223 kilonewton per meter according to Rankine's method. So all the time, usually, Coulomb's method show a little bit higher pressure than Rankine's method. Okay, so many times there is a criticism that Coulomb's method is a little bit over conservative. Okay, so thank you for watching.